Simple harmonic motion is one of the most tested topic in UTME JAMB. And in this video, I'm going to be explaining everything you need to know as far as the calculation is concerned. Now we start by the definition. The definition of simple harmonic motion is a motion that is periodic in nature and it happens about a fixed point such that the acceleration is proportional to the displacement of the body. But in all of this definition, what I'm really mostly interested in is that statement that says that the acceleration of the body is proportional to the displacement. But that's not the only thing. This acceleration is in the opposite direction to the displacement as well. So let's say this is the fixed point. What we have is that the acceleration is going to be directed towards the fixed point, but the displacement is going to be directed away from the fixed point. But apart from that, they are proportional to each other. And whenever we have a proportional sign like this, what we do is that we introduce the constant of proportionality. Just that in this case, our constant of proportionality is the square of omega, and omega in this place is called the angular speed. So I can rewrite this and say this is A equals minus omega squared x. And this right here is the general equation for any body in simple harmonic motion. You know, just like you have those equations of uniformly accelerated motion. For simple harmonic motion, this right here is the general equation for it. But it is also accompanied by the equation for the velocity of this body as well. So the velocity is given as omega multiplied by square root of a squared minus x squared. So in this situation, v is the velocity, omega remains the angular speed or angular velocity, a represents amplitude, and x represents displacement at any point. A, amplitude being the maximum displacement, and x represents amplitude at any point. So one of the things you want to know is that you want to know some special thing about a body in simple harmonic motion. That is, when a body has zero displacement or when a body has maximum displacement, what is going to happen to the speed of such body, and exactly what is going to happen to the acceleration of the body as well. So you can tell here that if the body has zero displacement, let's quickly see what will happen to the speed of the body. So velocity will be omega, then multiplied by square root of a squared minus, since x is 0 here, so you have 0 squared as well. And when you do this very well, you have omega multiplied by square root of a squared, which is omega a. At this point, v equals omega a. V being equal to omega a means that when the displacement is 0, the value of v is maximum. The value of v is maximum. That is why among one of the example of a body in simple harmonic motion is a simple pendulum. So if you have this now this point is the point where x equals to 0. That is the point of minimum displacement. And this point, they are point of maximum displacement. So you notice that if x equals to 0 here, that also implies that v is going to be maximum at this point. This is the point where v is maximum. And automatically, the kinetic energy is maximum at this point as well. So let's quickly go into that. Let's see what will happen to the acceleration at this minimum displacement. So going to our equation, a equals negative omega squared x. So a is going to be negative omega squared multiplied by 0. So what happens here? Acceleration is equal to 0. So at the point where we have minimum displacement x equals to 0, we see that the v is maximum for simple harmonic motion and the acceleration is equal to 0 at that point. Now let's proceed. Now let's take another point. This is the second point, that is at x equals a. When we have maximum displacement, what happens to the speed, what happens to the velocity at that point, and what happens to the acceleration? So in this case, we have v is going to be equals to omega square root of a squared minus, at this point now, x equals to a. So substituting a into this expression, we're going to have a squared. And if you look at this very well, a squared minus a squared is going to be 0. When you multiply 0 with omega, you're going to have 0. So v is 0 at this point. So at the point of maximum displacement, we see v being 0 here. And these are those 2 points, as you can see them here. The 2 points that we have here. So these points are points of maximum displacement. At those places, you have v equals to 0. Automatically, the kinetic energy is minimum at those 2 points as well. Now, quickly, let's go for the acceleration. Acceleration will then be negative omega squared a, because at this point x equals a. So what you notice from here is that acceleration is going to be maximum in magnitude, because this negative sign is actually showing the direction with respect to displacement. But when you take the magnitude, at this you ignore the negative sign, omega squared a is going to be the maximum acceleration. So you want to take note of that. You see that we have that at minimum displacement, v is what? Maximum, and acceleration equals to 0. And at maximum displacement, we see that v equals 0 and acceleration is maximum. The magnitude of acceleration is maximum at that point. So quickly, now that we're done with the two major equations that governs a body in simple harmonic motion, let's quickly look at some of the things that we need to know, especially about omega, which is the angular speed. Quickly, when we say angular speed is actually given by angular displacement over time. So angular displacement over time. But there's a special way we can tweak this. And the special way is that whenever we're dealing with anything angular has to do with periodic in nature. It's like somebody going in cycles. Now, when somebody is going in cycles, the time taken for them to complete one cycle is known as the period of the body. The time taken to complete one cycle, one revolution, one oscillation. Whenever you hear any of these things, the time taken for this to happen, for one of them to happen, is called the period of the motion. So when you know the period of the motion, what will be the angular displacement at that time as well? So when you have completed a period, the angular displacement is actually one revolution. And one revolution is the same thing as 2 pi in radians. You want to take note of that. One revolution is the same thing as 2 pi in radians. So I'm going to use these two information now. That implies that omega can be re-expressed as, so instead of me just writing ordinary theta here, what if my theta was 2 pi rad? If my theta was 2 pi rad, then that would be divided by, I know that my time for 2 pi rad, which is one revolution, is actually the period of the motion. So 2 pi over period. So from this place, we see that omega is always going to be 2 pi divided by period. And next thing again is that this is similar as 2 pi multiplied by 1 over period. And 1 over period is the same thing as frequency. So we can see two expressions here. Omega is 2 pi divided by period, and omega is also 2 pi multiplied by frequency. So take note of this equation. Now, all these equations, they are very, very, very important in some of the things that we're going to be doing. And so quickly, let me jump into the concept of simple pendulum and the helical spring. Simple pendulum and the what? And the helical spring. So let me quickly explain what goes on there and the equations that we'll be needing. So for the simple pendulum, I already spoke about it earlier. So let me just quickly sketch it here. So if this is representing the simple pendulum, so let's just have it here. Yeah. So we have this, we have the bulb here. Now let's see what happens with a simple pendulum. For a simple pendulum, we're going to be considering the displacement. So don't forget the general equation for a body in simple harmonic motion. The general equation is that A equals negative omega squared x, where x is the displacement. So in this place, because the body is actually going to be released from this point, and it's going to be swinging under the influence of gravity. It's going to be swinging under the influence of gravity. So for this case, we're going to be using negative the value of g for gravity here. So that implies the acceleration in this place is minus g, and the displacement is actually going to be taken as the length of the pendulum. So we have negative g equals negative omega squared L. So when this negative sign cancels out, so we have that g divided by L equals omega squared. And what do we have here? It implies that omega will be square root of g over L. So for a body in simple harmonic motion, the omega, the angular speed, equals square root of acceleration into gravity divided by the length of the pendulum. And these are the things that the angular velocity depends on. Don't forget earlier, we had gotten expression that omega equals 2 pi over period, and omega is also equal to 2 pi f. So I'm going to bring those things down here, 2 pi divided by period. By the way, this also means that period is 2 pi divided by omega, and the last one was omega equals 2 pi f. So I'm just going to substitute this omega into this expression now. So you can see that we have here that period is going to be 2 pi, everything divided by square root of g over L. And so if you do that very well, this one also is going to be omega equals 2 pi. So we have omega. Omega itself is square root of g over L, and that will be 2 pi f. So that implies that from this place, I can say t equals 2 pi. So when you do this, this will go up and g will remain, square root of g will remain down. So you have square root of g divided by, square root of L. L will be up and g will be down. And this one implies that frequency equals 1 over 2 pi square root of g over L. So these particular two equations work for a body, a simple pendulum, which is a body in simple harmonic motion. And what you notice here is that the length is what this guy depends on. The period of a simple pendulum depends on the length. So as you increase the length, the period also increases. But as you increase the length, the frequency decreases. As you increase length, the frequency decreases. So please take note of that. Increase in length causes decrease in frequency. And this is the relationship for a body in simple harmonic motion. Specifically now, simple pendulum. It only depends on the length. It only depends on the length. And from here, you can easily compare that the period for a certain time divided by length for a certain time is going to be the same thing as the ratio of the period for a certain another time and the length O for another time. That is just based on the constant proportionality that goes on in this place. Now, quickly, you can do that same thing for frequency. I'm done with simple pendulum. Let me quickly talk about the helical spring. For the helical spring, it looks something of this nature. So the helical spring looks something of this nature. Of course, you can be dragging a certain force here. If you remember from Hooke's law states that F equals minus kx. K is the force constant. X is the displacement. This one is the force constant. And F itself is the force. So from this place, you notice that you can easily say that force equals MA. MA equals negative kx, like that. So from this place, that implies that A equals negative kx, everything divided by m. And don't forget earlier, under simple harmonic motion, that acceleration is given as what? Negative omega squared x. So that implies that I can equate this thing to negative omega squared x. So if I compare these two equations, the negative sign can cancel out and the x part can cancel out. So you write that omega squared equals k over m, and that implies that omega equals square root of k over m. And do not forget that omega itself is 2 pi divided by period, and we know that period is 2 pi divided by omega, and omega equals 2 pi f. So if I substitute everything back into this place, so that implies that period will be 2 pi divided by omega. Omega now is square root of k over m, and that implies that period equals 2 pi square root of m over k. And similarly, omega, which is what? Square root of k over m equals 2 pi f. And this implies that the frequency is 1 over 2 pi multiplied by square root of k over m. So you notice that just like we did for the simple pendulum, we now have an expression for the period and for what? And for the frequency. These are the expressions. In this case, the period depends on the mass of the object and also on the force constant in the spring. So the mass, so in simple pendulum, it does not depend on the mass of this bulb. No matter whether this mass is big or it is small, it does not matter. It only depends on the length of the pendulum. But when we go to the helical spring, for the helical spring, the period depends on the mass of the object and the spring constant. Whereas in this case, it depends on the length and the acceleration due to gravity. And this right here, everything in this video, these are the things that you will need for proper calculation and to understand everything that is going under simple harmonic motion in your UTME exam. In my next video, I'm going to be solving real questions, real UTME past questions on this particular topic. And which is why I would like you to subscribe to my channel, like and comment. You can even comment the particular question you want me to solve, and I'm going to be making video about it. So do well to click that bell button and subscribe. I'll see you in the next one.